yeah, I can draw the tree. No, I put these slides up. I always draw stuff. That's all right. Let's see. Let's say we have an inverter. And we put an input. This is like V in. This is V out. V in goes like, I'm gonna make it go low. V in, this is V out. I'm gonna put a capacitance on here. So in real life, it takes some time to charge up that capacitance, right? So it would look more like this. And I'm going to kind of approximate this. I'm going to sort of say, you know what, it's kind of like it's got this exponential thing, but I'm just going to approximate it by this straight line. Okay. And I'm also going to introduce something that you need to know. So this output waveform, there are some things that we define for it, which you may have learned before. Let's just blow this up. Let's say it goes like this. Oh, I can't blow it up. Never mind that. Never mind that. Oh. Yeah, I'm gonna hold on. I'm gonna make this bigger. I don't like this. Let's make this bigger. So here's our input. Oh, I had the other way, didn't I? And here's our output. This is V in, this is V out. So we need to define a few things first. There is a thing called the rise time and the fall time. And the rise time is this time. And let's say this was, we'll assume this is 1 volt for now, and this is 0 volts, okay? So the rise time is usually defined as from the 10% level to the 90% level. Okay, sometimes it's 2080, sometimes people use 1090. I'm going to use 1090. So this would be like from 0.1 volts to 0.9 volts. That is called T rise. Okay, and similarly, we have from the 90% to the 10%. So 90% down to the 10%. We are going to call T fall. That's the fall time. You guys learned about this before? And if, let me just make a little slope on these. We also have another term that's very commonly used is to go from the 50% of the input to the 50% of the output. So that's 50% of the input to 50% of the output. And we're going to call this the delay time, T delay. And in this case, the output's going from low to high. So it's the 50% level of the input to the 50% level of the output. And similarly, we have from, is this what we measured in lab 1? Yeah, you guys might be measuring this in lab 1. We have 50% from the input to the 50% output when the output's going low, And we'll call that T delay high to low. Did you guys learn this before? These are the common waveform parameters. Rise time to fall time. There's the delays, high and low. And sometimes if T delay low to high equals T delay high to low, we just call that T delay, TD. And in fact, TD by definition is equal to T delay low high plus T delay high low over 2. It's just the average of those two numbers. And when they're both equal, then they'll all be the same. Everybody okay with that? Okay, so now go back to our waveform. So we had this input that went like this. The output.
Could you go back to the last page just for a quick second?
Yep.
Or did you? Yeah. Okay, perfect. There you go. Thank you.
Let me get rid of some of these old. Got too many pictures here. Don't crash. Crash and burn. All right, let's go over. So I said, yeah, this kind of goes up like this.
Professor, could you please go back quickly?
Sure. Got a question, or you just want to look at it?
I just want to look at it.
Prof, in your circuit's drawn, the Z stands for Z? Where's Z? Like in previous slides? Z was just like over here. I don't know. I just called Z the output. That was the name of the output signal.
So I have a question in the last, the one next. Yes. So we call the time according to the output. We call the low to high for
Yeah, on the output.
Right?
On the output.
Okay.
You guys are asking lots of questions. I love it. Love it. Okay, so we had this input, we had the output. I said it's normally because, like, you know, basically we have this inverter charging a capacitor. And we know that when you have some current, in this case, the current will be coming here charging, we get this exponential, but I'm going to simplify it. And I said, I'm going to just make this like little straight lines. So I'm going to assume this kind of looks like a straight line, and that looks like a straight line. And I'm also going to make another assumption. I'm going to assume that this input changes really fast, okay? So the 50% point is like the time and when it occurs, right? And if this is a straight line, I'm going to assume this 50% is right here, right? So I'm going to, this is like my sort of simplified version where I'm measuring the delay, right? T delay, low, high. And likewise over here. This is my T delay, high, low. So I need to use some, excuse me, some equations here. I'm assuming that the transfer function here is a straight line. So we know from our basic circuits that I, the current charging a capacitor, equals C dV dt, or delta V delta T, right? Remember that equation you learned for current and capacitance and voltage on a capacitance, right? And in this situation, I'm going to call this my capacitance here, and this is my current my inverter is going to provide. And let's say, you know, I'm normally charging up to VDD, right? So in my case here, I can say I equals C. Now the delta V I'm trying to measure here, this is VDD. So that point at the 50% is VDD over 2. Right? I'm assuming it's a straight line. So my delta V, I'm trying to find this delay between this T delay low high. The delta V is going to be VDD over 2. And then the T is what I want to find here. That's this T delay low high. And so then I can, if I try to solve for delay low high, T delay low high is going to be equal to C VD over 2, and then I'm going to bring the I over the other side, 2 times the current. So now I have a simplified expression, the delay in this circuit, charging this capacitor, and we can do the same. It's the same for T delay high low. The same. T delay, if you want to call it, or we'll just call that equal T delay, is just equal to the capacitance times the supply voltage over 2 times the current. And we're going to use this equation. This is our equation we're going to use for generating delays, figure out, approximating delays in circuits. You can always use your simulator like you've been doing in lab 1 to exactly figure these, but when we want to do simplified calculations, this is an expression we can get for the delay of a circuit because we're interested in the delays and we're interested in the power. Everybody okay with that?
So what is the value of the current? Like
Well, we need to calculate that. We learned our equations for circuits. So when we know the size of the transistors and everything, we can figure out the current and the voltages. We already learned that, right? I don't know, I could probably delete them, but remember we did a problem. I said, calculate the currents. We got these microamps of currents in one of your bonus questions.
like the KMW over L?
Yeah. Yep, that whole thing. So we know how to figure out currents already. And so as long as I give you the capacitance of the supply voltage, you can figure out the delay. Let's go back here. So that's where this equation comes from. The delay of a circuit is a CVD over 2I. The energy dissipation of a circuit, if you remember, you learned in your physics class or whatever, it's CVD squared, right? And the power of circuit is the energy per unit time, or it's the energy times the frequency. So it's CVD squared F. So now we have these two equations, one for the delay and one for the power. And those are the two most important things we want to know for any circuit. So if you're given the frequency of operation, how much it's charging and discharging. And by the way, this power, we call it the AC power or the dynamic power. And it comes about because what happened in this circuit, I charged down and I charged up. What happened was first, I charged up this current. Some current ran in and charged up this capacitor, sorry. That was this part of it when it went high. And then when this went high, the output went low, and then the current went down this way. So if you look at this battery, say we had a battery over here or a power supply, what's happening is it takes some time, but some current goes through there. Like we actually literally have current going through there. We're charging and discharging, but there's current going around here over time. And the faster the frequency we do it, the more times this current goes around here. So that's this, the higher the frequency, the faster we charge and discharge, the more power, and the power is related to this capacitance and the voltage. Interesting, this is voltage squared. So if you really want to reduce the power, a great way to reduce the power is reduce the voltage. If you reduce it, like if you cut the voltage in half, you got 1/4 of the power. It's linearly related to the frequency of the capacitance. So lowering the capacitance, lowering the frequency, or lowering the voltage reduces the power in our circuits. So we're always trying to lower the C. That's why we move to smaller technologies because the load capacitances are smaller. But we usually like to go at faster frequency. So this is usually going up as we try to go faster with newer technologies. This is usually going down because the capacitance of the transistors go down. And what you'll see as technologies improve, this VDD has been going down as well to help reduce the power. But this is a real major limitation of our circuits, the power consumption, because like I said, you've got this chip that's like the size of your fingernail and you're trying to put hundreds of watts in it and it heats up and it'll destroy itself if you get too much power. Anyway, these are two important equations for the power and the delays in our circuits. And now it's time, bonus time.